Welcome back, Virtual Earth Science. Today's mystery, what does this train have to do with astronomy? What you're hearing, that change in pitch, it's called the Doppler effect. It's a change in the frequency of a wave, in this case a sound wave. The frequency of a sound wave is like the pitch. When the train was approaching, it had a high pitch, and as it passed us, the pitch changed from high to low. You know what I'm talking about, right? I'm sure you guys have heard that before, from a car or a bus or a train. So the Doppler effect is this change in frequency of any wave. It could be a wave like sound, or water waves, or light waves, and it's caused by the motion of the wave source, or by the motion of the observer. So if I ran away from the train very fast, I would also hear the frequency change. And so we can say that very efficiently by saying it's caused by the relative motion of the wave source and the observer, as long as we're moving away from each other or toward each other. The wave source in this case being the train and me being the observer. So that's the Doppler effect. This picture is one way I can try to show you why the Doppler effect happens. The center of the circles there, we can think of that as the source of the sound waves, or of whatever waves we're talking about. And this source is moving to the left in this picture. And because it's moving as it puts out these waves, the waves travel out in every direction, but you can see that in front of it, it's moving to the left, right? In front of it, the waves are squished together. And behind it, they're stretched apart. The frequency of a wave is like the pitch for sound, but the frequency describes how closely together these waves are compacted, how frequently the waves pass. So in front of this thing, on the left, there's a high frequency because the waves are squished together. And behind it, on the right, there's a low frequency because the waves are stretched out. High pitch on the left, low pitch on the right. And so this is a visual way to see the Doppler shift. Here's another very similar picture. This time the fire engine, the source of the sound, is moving to the right. And the observer, that funny guy in the black and white picture, is on the right side. Not moving, the fire engine is moving toward him. And you can see how the waves are squished together and have a high frequency in front of the fire engine, this time on the right, and have a low frequency, they're stretched apart, behind the fire engine, this time on the left. And now a physics teacher in the UK is going to explain to us different aspects of the Doppler effect in different situations. Enjoy!
A duck swimming in a pond makes waves. As it swims forward, it catches up with part of the waves and leaves some behind. Those in front of it are bunched up and have a short wavelength. Those behind are stretched out and have a much longer wavelength. Remember that frequency and wavelength are related, and therefore a short wavelength gives a high frequency. Unfortunately, I couldn't catch a real duck, so let's try that with a model. As the duck bobs up and down and moves forward, the waves in front have a short wavelength, those behind have a long wavelength. I hope you appreciate the effort that I put into this. I got wet, muddy, and my welly fell off. The waves arriving at the edge of the pool in front of the duck will be closer together and so more frequent. Another example which you've probably noticed before is the noise from a car. As the car moves forward, the sound waves in front of it bunch up and those behind stretch out. So the note of the engine in front of the car is slightly higher than that behind. Therefore, as the car passes, we hear the note change. When an object moves very, very fast, we can see the Doppler effect in the light it emits. Observation of the light from distant galaxies is of key importance. If the galaxy was moving very fast towards us, then the light from it would be slightly bluer. If it was moving very fast away, then the light from it would be slightly redder than we'd expect. Making these observations, we look for characteristic patterns that all galaxies and stars emit. And, as here, our observations show that from practically all galaxies, the light is shifted towards the red end of the spectrum. That implies that all galaxies, or almost all galaxies, are moving away from us rather than towards us. This is a key fact in support of the Big Bang theory. The degree to which the spectrum is shifted depends upon the speed of the galaxy relative to the speed of light. Providing that the speed of the galaxy is not a large proportion of the speed of light, the equation which relates the redshift to its speed is a fairly straightforward one.
Cool, I learned a lot from that, I hope you did. So he told us that light can even be subject to the Doppler effect, and that if something like a distant galaxy is moving fast enough, in fact it has to be moving a substantial percentage of the speed of light, which is, 300,000 kilometers per second. So if it's moving anywhere near that, then the frequencies of light that it emits will be Doppler shifted. They will be subject to the Doppler effect. Now you guys, working through those web pages, learned about the fact that different elements absorb or emit specific colors of light. And this diagram is trying to show how if a star in a galaxy far, far away was emitting a spectrum like the one we see on the right side of this diagram, and if we compare that with the spectrum of a particular element, say hydrogen, that we know that this star is mostly made of, and if we look at that hydrogen in the laboratory, it might look just like the spectrum on the left side. And from that comparison, we could conclude that all of the absorption lines, those black lines that hydrogen is supposed to show, are there in the star's spectrum on the right, but they've all been shifted up, in this case, toward the red. They've all been red shifted, we say. And so we can conclude from that this star must be moving away from us at a tremendous speed. And we can actually figure out, by measuring carefully what the differences are, we can figure out exactly how fast this thing is moving. And that's one of the things you're going to do in the activity I have for you after you watch this video. Once again, if we have the unshifted spectrum up at the top, hydrogen as we would observe it in the laboratory when it's not moving, hydrogen coming from a star in a galaxy that is moving away from us would emit a red shifted spectrum, shifted towards lower frequencies, and red has lower frequency. Hydrogen in a star in a galaxy moving towards us would exhibit blue shifted frequencies. All of those black lines are shifted toward the blue or purple side of the spectrum, higher frequencies. This next and final video clip is kind of funny. It starts out by sort of making fun of you. Please don't take any offense. It has a lot of cool stuff in it, so please try to pay attention and enjoy the humor, I hope. Good luck on the activity.